Similar to what we said in the section on double integrals over polar regions, if you were to take the double integral of 1, you would get the area of the region in question. Now, through a similar logic, we can express a volume as a triple integral. So normally, when we take a triple integral over a solid E, we would be calculating a hypervolume. However, if I take away one of those dimensions in the form of the function, and just say let's do the triple integral of 1, then essentially what we're doing is saying take the volume of E and multiply everything by 1. So numerically, this is going to be equal to the volume of E. We'll use V of E for that notation. Now, occasionally this works out really nicely if you need to use the cylindrical or spherical coordinate system to calculate the volume of one of these solids. So, as an example, find the volume inside the sphere x squared plus y squared plus z squared is equal to 100, but outside the cylinder x squared plus y squared is equal to 25. So inside the sphere, but outside the central cylinder. So this is, for all intents and purposes, saying take a ball with a diameter of 20 units and take a drill with a radius of 10 units and drill straight through the center of that ball. Determine the volume of the resulting ring. So first thing I'd like to do is have us take a look at the XY trace so that we can see how round this thing is. Now x squared plus y squared is equal to 25. That's going to be a circle of radius 5. And if we take a look in the xy plane, we're going to see x squared plus y squared is equal to 100, which is going to be a circle of radius 10. So within the xy plane, this is what our region would look like. Or we're considering the region that's between these two things. And now I need a donut. That figures. As soon as I start doing a math problem, I start thinking about food. Now, given that we're dealing, once again, with round things, I would say that a conversion into polar coordinates probably seems appropriate. So convert to polar, or technically cylindrical coordinates. So x squared plus y squared plus z squared is equal to 100. Can be replaced now. X squared plus y squared will become r squared. And in spherical coordinates, we would be dealing with a circle of radius 10. For our cylinder, x squared plus y squared is equal to 25 would be converted into simply r squared is equal to 25. And taking a square root of that, that is simply going to be r is equal to 5. So if we were to analyze this thing within the RZ trace, we would see the following. So first off, circle with radius 10. So circle with radius 10. And r equals 5 would simply look like a vertical line. Now the portion of the solid that we would be looking at would be this part right here. As you can see from the XY trace, everything that we have here is between a distance of 5 and 10 units away from the pole. So we're looking for between 5 and 10 units away from the pole. I'm fairly confident that we would be able to set this up using either cylindrical or spherical coordinates. So I'd like to start by setting it up using cylindrical coordinates. Cylindrical. So in cylindrical coordinates, we would want to bound z first, then r, then theta. Now it appears as though z is going to be bounded above by the top side of the sphere and below by the bottom side of the sphere. I think an argument could be made, though, that we could just figure out the volume above the xy plane and double the result. But since I'm, like I am, let's go ahead and solve for both halves of the sphere. So that'll be the positive square root of 100 minus r squared and the negative square root of 100 minus r squared. R, we can see from the xy trace, is going to start at 5 and go out to 10. Or within the RZ trace, we see that it starts in 5, it goes out to 10. Theta is going to be one full trip around the Cartesian plane, so that'll be from 0 to 2 pi. Now, if we are interested in the conversion into spherical coordinates, we could certainly do that as well. So first off, r squared plus z squared would give us our outer bound. R squared plus z squared in spherical coordinates would be rho squared. So that would be rho is equal to 10. Now, as far as phi is concerned, here's what we're going to see for phi. Phi is going to start here, and it's going to go out to here. Now that, of course, would be the intersection of the sphere with the cylinder. So for the intersection of the sphere with the cylinder, we're going to find intersection. Of r equals 5 and rho equals rho, not beta, rho equals 10. So r equals 5 would technically be considered rho times the sine of phi. We're saying that's equal to 5. But then we're also saying that rho is equal to 10. So this would be 10 times the sine of phi is equal to 5. Solving for the sine of phi gives us sine of phi is equal to 1/2. And we're looking for one acute angle and one obtuse angle where that takes place. That's going to be phi is equal to pi over 6 and 5 pi over 6. Now you'll also notice through our region that if we were to start at the pole and work in an outward direction, that phi is actually going to be an outer minus inner kind of motif here. The outer being the sphere, which we got as rho equals 10. The inner is going to be the cylinder. So as far as the cylinder is concerned, that was r is equal to 5. So rho times the sine of phi is equal to 5. Solving this for rho gives us rho is equal to 5 divided by the sine of phi, or more succinctly, 5 times the cosecant of phi. So in setting up all of our bounds in spherical, hey, we have some space over here. Spherical. Rho would be bounded below by the cylinder, 5 times the cosecant of phi, and above by the sphere, 10. Phi, we figured out the bounds on phi down here. That was from pi over 6 to 5 pi over 6. Theta will be the same in spherical as it is in cylindrical. So I'm going to set up both of these triple integrals and then make a decision on which one I would like to actually proceed with. So, the volume in question is going to be the triple integral over the solid E of 1 dV. We'll set up cylindrical first. This is going to be equal to the integral from 0 to 2 pi, from 5 to 10, and from the negative square root of 100 minus r squared to the positive square root of 100 minus r squared of 1, and then dv in cylindrical would be r dz dr d theta. Now, first integral is usually the most straightforward. We'll just wind up with a couple of radicals in here, and then I think a u substitution right after that would be appropriate. In spherical coordinates, this would be integral from 0 to 2 pi, integral from pi over 6 to 5 pi over 6, that was for phi. And then the integral for rho, we said was going to be 5 times the cosecant of phi up to 10 of 1 times dv is going to be rho squared times the sine of phi times d rho, d phi, d theta. Now I think in both of these cases, we're going to have a bit of a challenge in front of us, but I think it's going to be doable in either fashion. I think I would like to try this one out in spherical, and as a practice problem, I think you all should try this one out in cylindrical. So in spherical coordinates, I'm going to integrate first with respect to rho. So first two integrals stay the same for the time being. And we will see 1/3 rho cubed. Sine of phi stays the same, going from 5 times the cosecant of phi up to 10. And we'll see a d phi d theta after that. Simplifying this, we'll see a 1/3, we'll see a sine of phi, and we are going to see 10 cubed minus 5 times the cosecant of phi quantity cubed, d phi d theta. A little bit more algebra needs to take place here, and I'm going to factor the 1/3 outside of the remaining double integral since it is a constant multiple. So 1/3 times integral from 0 to 2 pi, and from pi over 6 to 5 pi over 6. When we cube the 10, we're going to get 1,000. Distribute the sine of phi to it. That'll be 1,000 sine of phi. When we cube the 5 cosecant of phi, we're going to get 125 cosecant cubed, and the sine of phi is going to cancel out one of those cosecants. So this will be minus 125 cosecant of phi squared. Now, something that I like that can now take place is the fact that we can factor this integrand into a function of phi times a function of theta and use Fubini's shortcut. Fubini's shortcut says, let's break this up into the definite integral from 0 to 2 pi of all of our thetas, which is just d theta, and then multiply that by the definite integral from pi over 6 to 5 pi over 6 of 1,000 times the sine of phi minus 125 cosecant squared of phi d phi. First integral is going to give us a measly 2 pi. Second one is going to give us something considerably beefier. 1,000 sine of phi, I believe that is going to be negative 1,000 cosine of phi. And then we'll see a plus 125 cotangent of phi. A couple of oldies but goodies from back in Calc 1. I also want to make sure that this is right, so I'm going to differentiate this. Differentiating cosine gives negative sine, so that'll turn the negative positive. We're good there. Derivative of cotangent is negative cosecant squared, so negative cosecant squared. All right, feeling good about that. Let's plug in these bounds, see what happens. So this will be negative 1,000, and we're going to shortcut this a little bit. Cosine of 5 pi over 6, that's that way on the unit circle, that's negative root 3 over 2, plus 125 times the cotangent of 5 pi over 6, that's going to be negative root 3 over 3. Minus, plugging in pi over 6, this will be negative 1,000. Cosine will be root 3 over 2 plus 125 times the cotangent of pi over 6. Wait, cotangent of 5 pi over 6, that's just going to be negative square root of 3. And then this one will be positive square root of 3. Good, now everything here has a square root of 3 in common. That's exactly what I wanted to see. All right, now we just got to get our pluses and minuses right. So 1/3 of 2 pi times Negative negative is positive. 1,000 divided by 2, that's going to be 500 square roots of 3. Minus 125 square roots of 3. Minus a minus is going to be plus 1,000 over 2. That's going to be, once again, 500 square roots of 3. Minus a positive, so minus 125 square roots of 3. Now I'm really starting to suspect that whole, we could have just doubled it by starting at 0. That's really holding true here. So let's see, that's 500 plus 500 is 1,000, minus 125 minus 25 is 750. 1/3 of 750 is 250, times 2 is 500. So final answer for this one, 500 pi square roots of 3. That is hot. So as a practice problem, see if you can try this out in cylindrical coordinates and see if you wind up getting the same result as I do. And that'll be a really good practice problem for you.